Hello everyone. Today I'd like to talk about the Internet Checksum. And this is something to make sure that data that we've sent hasn't been corrupted. So it's something we can look at that hopefully will indicate if something has gone wrong. And it shows up in a few places in the network stack. So let me first grab some traffic and I'll show you where it shows up, and then I'll explain how to compute it. So if I pop into my terminal here, I'm going to launch something called mininet, which is going to create a virtual network that I can experiment with. And so it's just going to be a host connected to another host via a switch. And so I can send traffic directly from one host to the other. And so I see here, okay, I've got this host 10.0.2.2. So from H1, let me send some UDP traffic. So I'll say, hello, everyone, exclamation mark. I'll send that to dev UDP 10.0.0.2 and to port 60,000. Doesn't really matter what port it is because I'm not actually trying to receive a message here. I just want to generate a little traffic. So let me open up and Wireshark the first host here, start capturing, and then I'll go and send that message. And I see that generated a UDP packet going out from my first host to my second host, going to port 60,000 as I planned. I do get an ICMP message back that says destination unreachable, and that's because nothing is listening on the host, but I don't really care. I actually just want to look at the bytes of the traffic here and get a handle on that. But I see, as promised, this is sent over a UDP packet. The payload is 16 bytes, hello everyone, exclamation mark, and then a line break there. But let me start by looking at the internet header here. So the IPv4 header in this case has a field called checksum, which comes right before the source address and the destination address. So let me I want to copy out these bytes into Python and have a look at them. So here I have my IP header. So I'll say the bytes are from hex this. Okay, so there's my IP header. If I get my checksum out, I know that is right before the source address and destination address. These are each 4 bytes, so I know this actually starts 10 bytes before the end. So let me just check this real quick. Whoop. Of course I have to say IP header. Okay, so 969F, let's just check. Was that the checksum here? Yep, okay. So that's something I'm going to show you how to compute in a moment, but I just want to make sure I had it. Let me also copy over the UDP header here. So here we go. So here's my UDP header. And then finally, I'll copy over my payload, which I already know what it is. It should be hello or hello everyone with a line break. But I'll just go ahead and copy it from here anyway. Okay, so that is everything. Great. Okay, so now I'm just gonna analyze these a little bit. So the question is, how do I compute this checksum from this data? And the idea is, okay, I'm going to look at all bytes except for the checksum itself, because that wouldn't make sense. I'm trying to compute the checksum. I can't know the checksum before I compute the checksum. But all 2-byte words across the IP header and everything that comes after it, except for the checksum, I'm going to add them together and look at the 2-byte remainder, what's left, because there's probably going to be overflow here. And that 2-byte remainder is going to be the checksum. But there's something special that I have to consider when I'm doing this addition, because the addition actually uses what's known as 1's complement. In fact, if I look at, okay, so the UDP header itself also uses the same checksum. And the way they explain it sounds crazy. It says, it's the 16-bit 1's complement of the 1's complement sum. Okay, well what the heck is a 1's complement of a 1's complement sum? Okay, first let me explain the 1's complement sum. So I'll do it using 8-bit, just to make it easier for me to write here. So we'll think about 8-bit 1's complement ints. So 1's complement is a way of representing both positive and negative numbers with a fixed number of bits. So as an example here, if I had the number, let me say 0, 1, 1, 1, 0, 1, 0, 1. So if I look at that number, that is actually going to be 117. And then the way to get the negative number is just to invert each of those bits. So if I go 1, 0, 0, 0, 1, 0, 1, 0, that is going to be a negative 117. And just to give you one more example here, let's say that I had the number 0, 0, 1, 1, 1, 1, 0, 0. Okay, so that number is going to be 1, 1, 1, 1, 0, 0. That is going to be 60. And so the negative 60 would be 1, 1, 0, 0, 0, 0, 1, 1. So one thing we observe here is that negative numbers all have a 1 in the most significant bit, and positive numbers all have a 0 in the most significant bit. But what about 0? Okay, so what if I start with 0, which would just be all zeros, right? And what would be the inverse of that? Or what would be the inverted bits for that? Well, it'd be all 1s, right? And what's negative 0? It's still 0, right? So this is kind of the weird thing about 1's complement. It's actually a little bit of a redundant representation because it has two different bit patterns that are a 0. Unlike 2's complement, which actually only has one representation of a 0. So 1's complement allows us to represent numbers from negative 2 to the number of bits minus 1 up to 2 to the number of bits minus 1 minus 1. So in this case, okay, if I've got 8 bits, this is saying I can represent from negative 127 to 127. So negative 127 would be, oops, I should be careful here. That would be this. So this is negative 127. And positive 127 would be this. Okay. So that's the range here, whereas 2's complement can actually go from, I'll just say note, 2's complement, which I'm not going to go into detail on here, but just so you know, there's another system called 2's complement, goes from negative 2 to the b minus 1, to 2 to the b minus 1 minus 1. So instead of going from negative 127 to 127, it would actually go from negative 128 to 127. So it makes better use of the bits. It doesn't have two representations of 0. But for legacy reasons, as far as I can tell, we're using 1's complement addition here. So what that means is, okay, we have to do something a little bit special because of these two zeros here. And there's an issue that arises when we have overflow. So let's suppose we start with a 0. This is a 0. I know it's a negative 0, but it's a 0, right? And let's say that we add a 1 to it. Okay? Now, if you look at this, what's going to happen is, okay, 1 plus 1, that's going to carry over here, going to carry, 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 carry. And what we'll get is overflow past the most significant bit there. So this is going to overflow all the way over here. So let me just show, this is what we're doing. We're doing some addition here. So that is going to overflow all the way over. And usually what you do with overflow is you just cut off everything to the left. So we would just, so I'd say overflow, and I would cut everything off to the left, and I would just be remain with the 8 bits there. But there's an issue because supposedly I added 1 to 0, and I should be left with 1, but I'm not. So what I have to take into consideration here is I need to do what's called a wrap around add. So basically just add a 1 to that. All right? So when I detect overflow, I can think about it as, okay, I was adding something, and eventually it filled up as all 1s like this. That's a negative 0. And then I kept adding, 1 bit at a time. The first time I overflow, I have to add an extra 1. So if I detect that there's been overflow, I know that I need to add an extra 1 to whatever the result is. So let me do one more example here. Let's say that I started with this, and then I added this. Okay. So in this example, I would end up with, so let me start on the right here. So this would be a 1, and then I would have that whole thing with the carries all the way through. So this is adding a 3 to a -1. Actually, this is -1 if you look at it. So I know I should be getting 2. What I actually get here is this overflows like this. Oh, let me just get this all lined up here. So this overflows, and what I would do is cut off that 1 on the end, and then add a wraparound 1. And so this should make sense because when I add this together, I get a +2. So actually, maybe I'll label all these. So this was adding a +3 to a 0. When I did the overflow and I truncated to the left, I was left with just a 1. But then I have to add this +1, so 1 + 1 is 2, as we all know. And so that's the correct result. Oops, sorry, this started off as -1. There we go. This is a -1. So -1 + 3 is 2. Perfect. Okay, so let's implement that in code. And so what we got to do is, for the IP header, we're going to be using all the 2-byte words. So now we're going to use 16 bits, 1's complement addition. And so I'm going to take all the 2-byte words except for the checksum. So let me split the IP header into 2 parts, one that's before the checksum and one that's after. So I'll say IP header 1 is equal to IP header from 0 up to -10. Let's say IP header 2, which is the source and destination address. That will be from -8 to the end. Okay, and so I'll say here in my checksum bytes, all the bytes that are involved in the checksum will be IP header 1 plus IP header 2 plus UDP header, plus payload. Okay, so these are all the bytes I need to add together. So I got to take these out in 2-byte chunks. So I can do that in Python with the help of the struct class. I can say, okay, so I'll call them shorts. These are going to be unsigned shorts. I'll say struct.unpacked. Unpack. So I want to take out, so capital H means half or unsigned 2-byte words. And I want to take out as many of these as there are. Okay, so actually I'm going to say I want as many of these as there are the length of the checksum bytes. Oops, checksum bytes over 2 because, you know, there's 2 of these 2 bytes per every one of these words. Okay, so this is my format string here. I'm going to tell I want to unpack into these shorts here, and let me pass along the checksum bytes. Misspelled something here. UDP header. Struct. Forgot the T. There we go. Okay. So here are all the numbers that I need to add together. And so I'll do that in a loop. Let's say for short in shorts. I'm going to say S is equal to S plus short. But now I have to try to detect if overflows happen. So I'll say if, I mean, there's a few different ways to do this, but luckily the Python ints are much more than 16 bits, so they won't actually overflow. It'll just go into the bit number 17 position. So what I can do is look at it and say, okay, if I try to mask out the least significant 16 bits, so that would be like this. If that is not equal to S, then I must have overflowed because I have something that's not in those first 16-bit positions. So overflow has happened. So what we'll do is we'll mask. So I'll say S is equal to S and 0 to F. So that's the cutting off everything to the left. And then we'll do the wraparound 1, as I was discussing above. Okay, and that's it. So we're just going to add all of those together with the 1's complement sum. And let's see what we get. So if I print this out in hex, then I will get, okay, 4656, which this doesn't actually look like the checksum. But there's one more thing that I have to do, which is I'm supposed to take the 1's complement of this. Okay. So I have to take the complement one more time. So I'm going to say here S is equal to this and not S, or yeah. Okay, so this is the complement of S. Now, this is much more than 16 bits, so I'm going to have a lot of straggling ones to the left. So let me just and those out. Let's see if I got it. Okay, hang on. Something's not matching up here. Let me have a look real quick. Okay, there's a couple of things here. So one of them is I wasn't careful when I printed this out. I should have done it like that. Okay, but this is still not the right hex code. I look back and I realized, okay, the checksum in the IPv4 header is actually just for the header. So I'm going to ignore the UDP header and the payload when I compute this. And then I get exactly the right thing. Okay, nice. So this might be a good thing to encapsulate in a method here. So I'll say def get checksum. So, pass along some bytes. Assume that they are evenly divisible. I guess if they're not, I should pad them. So yeah, so let's say parameters. So B's is an array of bytes, an array of n bytes. If n is not divisible by 2, we pad by a 0, just to make sure that we can take out an even number of, or a whole number of these shorts here. So say if len b's mod 2 is not equal to 0, then I'll say b's equals b's plus bytes 0. Okay. But anyway, so that should do it, and then I'll return the result. So now I have this encapsulated nice method here. All right, so when I run the method, everything checks out. Now also, it just hit me why I was a little bit confused about the payload being involved. Usually the payload is not involved. It's the responsibility of UDP or TCP, some transport layer protocol to have their own checksum. But sometimes, like with an ICMP message, there is no transport layer protocol. And so actually in the case of ICMP, the checksum in the IP layer actually includes the ICMP payload. So if I look at this error message that I got back, and if I take the IP header for that, so I'll say here IP header, I'll say get checksum IP header equals bytes.from hex, that, and then also get my ICMP message. If I get that payload here, that is actually going to be part of the checksum computation. So if I look at that and I compute the checksum, so let me print this out here. Got checksum, so to be the IP header not including the checksum, so that'd be 0, -10 plus IP header -8, just as I was explaining before. But now we're actually going to add on the ICMP to that. When I look at that, I get FD28. And does that match here? Do I see it? Where's the checksum? Whoops, that's in the ICMP message. Okay, yeah, the ICMP also has its own checksum. Okay, but yeah, turns out within the IP header, we have a checksum. There it is, FD28. Great. Yeah, so there's a lot of places that you could detect that you got this wrong. So yeah, in the case of UDP and TCP, even though none of that information is included in the IP header, they have their own checksum that validates their headers and the data associated to them. Okay, so unless it's an ICMP message, the IP header is only responsible for checking itself, and it leaves it up to the transport layer to validate everything else. Okay, and for UDP, if the checksum is wrong, then usually you should just drop the packet. For TCP, if the checksum is wrong, then you would ask for a retransmission. But then there's a question, well, how reliable is that for detecting if there's been a problem? So let's say that I was to take this data that I was just looking at. So we'll pretend it is an ICMP message here. Let's say that I flip one of the bits here, and then I compute this again. So I just flipped one of the bits. Then the checksum is different. Okay. I flipped it back, the checksum is the same. Let me flip this bit here. Checksum is different. Okay, so that's good. It seems like it's able to detect some bit flips. And in fact, this header is capable of detecting all single bit flips. But we have to be a little bit careful. If there's more than one bit that's wrong, it is possible that this checksum will say it's still correct, that the checksum will look the same as what we think it's supposed to be when we go to validate this. So let me pick out a couple 2-byte words here. So let's print this one out. Let me pick out this 2-byte word. And I'll orchestrate something here that is going to have a bunch of flips, but will actually have the exact same checksum. So, okay, I'll choose this one, and I guess I'll choose this one at the end here. So I'll put this here. And this is what they are in binary. Okay, so now if I look at this, I could say, well, what if I were to subtract 1 from this big old number here? And so that would cause this bit to flip to a 0 and all these bits to flip to a 1, right? So I would say, in this case, I'll say 0 for x, 0 b. Yeah, so what I'm going to do is flip a whole bunch of bits. So this is going to flip to a 0, this is going to flip to a 1, 1, 1, 1, whoop, 1, 1. Okay, so those are all going to flip to a 1. And then I say, I know I subtracted 1 from this big number, let me add 1 to this big number. And so that would turn this into, right now it's a 1, that would turn this into a 2. In hex, that would just be, yeah, so let me put that 1, 0 there. Okay, so I've flipped all these bits, and I've also flipped these 2 bits. So a lot more than 1 bit has flipped here. And let's see, though, does the checksum change? So if I were to change this to 4, 5, BF, instead of C0, and this to 0, 0, 0, 2, notice that I get the same checksum. And there are even cases where I can flip only 2 bits and still get the same checksum. So for example, if I were to flip the least significant bit of this, so that's a 0, 0, 0, 1, and I were to flip the least significant bit of this, so that's a 0, 0, 0, 0, that's only 2 bits that I've flipped overall, but this will have the exact same checksum. So in general, this can only detect single bit errors. It can only detect. Sometimes, more bits will flip and you'll be able to detect it, but in some pathological cases, you will not be able to. All right, so that's all I have to say for now about the Internet Checksum. I'll have you do a quick exercise, and then we'll talk about a stronger kind of checksum that is computed at the Ethernet layer.